Hello and welcome to what is guaranteed to be the best podcast on sound you have seen today. Now, sound originates as some type of vibration. All sounds originate from vibrations in objects. The vibration of the sound, the frequency of the sound, is going to match the frequency of the vibrating source that's causing the sound. Now, in the case of sound, the original vibrating object caused something larger or more massive to vibrate at the same frequency. In the case of musical instruments, sometimes it is a sounding board, which is like the body of the guitar, or it could be air. A reed or your vocal cords cause vibrations in the air in your throat or in the instrument that causes a sound that you hear. Now, the way the sound, sounds is called pitch. Things that have a high frequency have a high pitch sound, and things with a low frequency have a low pitch sound. Now, a young person with good hearing can normally hear frequencies of sound between 20 and 20,000 hertz. As you grow older, though, you lose your ability to hear that upper end frequency of sounds. Things such as blue whales, for example, communicate at frequencies below 20 hertz, and that's called infrasonic. Things such as bats that use echolocation communicate at frequencies up to 100,000 hertz. That is called ultrasonic, anything over 20,000. Sound is transmitted in what's called longitudinal waves. Also, they are called compression waves. The medium of the wave is actually vibrating along the same path that the energy of the wave is moving. It's a series of pulses. In the case of sound, it creates pulses in the air that eventually cause your eardrum to vibrate back and forth that sends a signal to your brain that you're hearing a sound. If you've ever gone into a room real quickly where all the doors were shut and you opened a door real quick and you saw a curtain move across the room or another door kind of jiggled, that's caused by pulses in the air. A sound wave, is a series of pulses. You've got where the air is compressed together, and then the areas behind that where you have low pressure regions. And just like we learned before, it's not the medium that travels, it's the energy. In this case, it's a pulse, but it's not the actual air molecules. They're just vibrating back and forth, sending a pulse of air across the room. So in the case of a tuning fork, as it's represented here, you can see the longitudinal wave, and instead of it appearing as a sine wave here, it's a series of compressions and what's called rarefactions. The compressions are where the air molecules are clumped together tighter, and the rarefactions are the areas of low pressure between that. And we can measure the wavelengths by measuring the distance from one compression to the next compression. The farther apart they are, the longer the wavelength. The closer together, the shorter the wavelength. And again, shorter the wavelength, higher the frequency. Longer the wavelength, lower the frequency, assuming the wave speed stays the same. Now, because molecules in solids are packed together more tightly than in liquids, and molecules in liquids are packed together more tightly than they are in gases, and because sound needs to have something to actually vibrate, you can't have sound without having some kind of source that's vibrating. Sound travels faster in solids than it does in liquids, and faster in liquids than it does in gas. And this is because sound needs to have molecules to vibrate. So again, the speed of sound is different in different things. Generally, it's faster in liquids than gases, and it's faster in solids than it is in liquids or gases. To test this, you can just simply tap on a table, then put your ear to the table and tap on it again and see which one is louder. Also, sound cannot travel in a vacuum. In space, no one can hear you scream. If you do not have air molecules to vibrate, then you have no sound. There's nothing to hear if there's no air to vibrate. That's how we detect sound, by molecules in the air moving our eardrums. If there's no molecules in the air to vibrate, there's no way to transmit a sound from one place to another. You can still have a vibration, but you don't get sound out of it. Sound also has a definite speed. If you see somebody strike a hammer from very far away, you'll see them hit it before you hear it. This is why you see lightning before you hear the lightning. Hearing lightning, by the way, is what we call thunder. Sound has a definite speed, and it's much slower than the speed of light. The speed of sound also depends on the temperature of the air. At 0 degrees Celsius, sound travels at about 330 meters per second. At normal room temperature of about 20 degrees Celsius, it travels at 340. This is because air with a higher temperature has molecules with more energy. They bump into each other more often, so it's easier to set them vibrating and get them to hit each other. Now, for things that are solid, it's elasticity that increases or decreases the speed of sound. Something that is more elastic, like a steel bar, it regains its shape real easily. It doesn't deform. It goes back to its original shape whenever it's compressed, even at the microscopic level, as opposed to something like putty that's very inelastic, which is why like a steel bar will transmit sound much better than a putty bar would. So the higher the temperature, the more elastic a solid is. The higher the temperature a gas is, generally the faster sound will travel through it. The speed of sound also depends on the mass of the particles that's vibrating when you're dealing with a gas. Something like helium, which is lighter than oxygen, will allow sound to travel faster than something that is heavier than oxygen. If a gas is heavier than oxygen, sound will travel slower. Now, in the case of your voice, and disclaimer, don't try this, this can be dangerous, but you've probably seen people inhale helium from a balloon and their voice is a higher pitch. That's because the helium is lighter than oxygen, so your vocal cords are able to vibrate more frequently because it's easier for them to vibrate, and that makes a higher pitch sound. If you were to have your vocal cords moving in a gas that's denser than oxygen, then it would create a lower frequency sound because your vocal cords have a harder time vibrating, and that makes a lower frequency. Now, do not try either of these because your body works much better when you're inhaling oxygen than other stuff, or air with oxygen in it than pure helium. Something else about sound is intensity, which sometimes we call loudness. It's technically not the same thing, but intensity is measured in units called decibels, and this is a logarithmic scale, kind of like the pH scale you learned about in chemistry. If you go from 10 to 20, it's just not going up by 10 units, it's going up 10 times. So it's going up exponentially, and this is just a measure of how intense a sound is. This is just a chart showing some common things and their decibel level. Now, things over 85 decibels can start to cause hearing damage. Here's just a little more information about hearing damage, loud sounds. It could be a really loud sound for a short amount of time, or not incredibly loud sound, but over a large amount of time can cause some damage as well to some of the organs inside your ear. The next topic is natural frequency. Everything has an object that it vibrates at with the least amount of energy. Everything. Parts of your car, bells, tuning forks, your radio. There's natural frequencies, which is the frequency that something is going to vibrate out at using the least amount of energy. So again, what we call the natural frequency is the frequency that an object is going to vibrate at the lowest amount of energy. It's like the frequency, the vibration it naturally wants to make. Now, there's also forced vibration. If you take a tuning fork, hold it to a table, and hit the tuning fork, it's louder than if you hit it when it's just held in your hand. This is the principle behind sounding boards on musical instruments. You pluck a string, it makes a vibration, it vibrates whatever it's attached to, which makes the sound louder and transfer more. So that people can hear it better. So this is forcing an object to vibrate. Again, this is the principle behind a guitar, an acoustic guitar. You have strings that would be really hard to hear if they weren't attached to the guitar's wooden body that is forced into vibration, allowing you to hear the sound. Now, if an object is forced to vibrate, but the frequency that it's forced to vibrate matches its natural frequency, the amplitude is going to keep going up and up. This is called resonance. This is like if you're pushing somebody on a swing and you're pushing them at the exact right time. Every time they come back and start to go forward again, you give them a push, as opposed to pushing them out of sync. If something is resonating, it's being caused to vibrate at its natural frequency. And as long as that natural frequency is forced upon it, it's going to keep upping its amplitude. Just a little slide here on tuning forks. And when a tuning fork is vibrating, it's actually making tiny compressions in the air, even though you can't always see it. This is an exaggerated view. Resonance is how you're able to use your radio. If you still listen to a radio adjusting of stations. When you adjust the dial on your radio, you are changing the radio's natural frequency. And if the natural frequency of the radio matches the frequency coming in from the radio station, the radio starts to resonate and it picks up that station, allowing you to hear the music on it. Now the last bit of this, interference, just like we talked about with general wave properties, waves can interfere to increase their amplitude, or waves can interfere to cancel their amplitude and destroy it. Same thing with sound. You can have two sound waves that are arriving in phase and it causes them to be louder. You can have two waves arriving out of phase and cause it to be softer or not heard at all. It's a pictorial representation in A of waves arriving in phase and B waves arriving out of phase. Person A is going to be experiencing the sound much better than person B because the waves are arriving out of phase, and he will be hearing possibly nothing at all if they're arriving exactly out of phase. And this is why auditoriums and theaters try to people design them so that the sound is constantly reflecting off the walls and the ceiling to avoid dead spots, to avoid waves hitting somebody that are exactly out of phase and causing them not to hear part of the sound. If they're constantly reflecting back and forth, there's a better chance that the people in there are going to experience the whole sound and that there will not be dead spots. Poorly designed theaters do sometimes have dead spots where waves will arrive out of phase. Now, if two waves are just slightly different in their frequency, then what you get is a beat pattern. Sometimes they interfere, sometimes they don't, and then there's various degrees within that. And it's heard as a series of beats where the loudness goes up and down, up and down. Here is showing you a 10 hertz signal and a 12 hertz signal. And when those are combined, their composite signal has a beat frequency of 2 hertz. So it's going to get loud, faint, loud, faint. This is the idea behind tuning objects. If two chords or two keys or two parts of an instrument that need to be tuned, one way that people can tune them is they listen for the beats and they adjust it until the beats disappear. At that point, the frequencies match. So if frequencies are just a little bit off, it will cause a beat pattern. If you adjust them to where there is no longer a beat, then that means those two frequencies have been tuned and they're now at the same frequency. This might be easier to see looking at these combs where the bristles are spaced apart differently on each comb, and when they're overlapped, you see the beat pattern where sometimes they are interfering constructively and sometimes destructively. So that's an example of a beat pattern. Well, that brings us to the end of this podcast on sound. Don't worry, there will be more podcasts coming up. This is not our last one. As always, look back through your notes, look back through this, look through your book, come to class with questions, enjoy learning about sound. May the mass times acceleration be with you.